Today we're going to look at some automatic wind loading and see its effects in real time on a pretty simple parametric frame and some other shapes. And to do that, the script automatically works out the force on the members. And to do that, it uses wind zones. And they're the zones determined to code. They're automatically generated based on the direction that the wind's hitting the structure. So to start off, we can visualize which surfaces experience load under wind. If I apply a north wind to this simple box, you can see I've got windward, leeward, and the sides and the roof as well. So obviously the face that has the biggest effect is where it's hit directly face on by the wind. It's the largest size of load. Then as the wind hits, it'll go upwards, it'll create some suction on the roof, and it will create some suction at the rear of the building. So you can see in these arrows the roof's facing up and the rear face is facing away from the building as it tries to suck that panel away and suck the roof upwards. And likewise on the sides, as the wind hits from this direction, it's going to try and curl around the building, and therefore it's going to create suction which pulls these side panels away from the building. Now obviously it doesn't really make much difference if I change the direction for a box, because it's pretty much all the same. So what happens if I have a slightly longer structure? So here I've got a longer box. If I apply the wind there, similar thing happens. However, this time you can see the front face is the same. The roof and the sides are a bit different, and the rear is the same. So what happens here is that as the wind hits it with full force on the face, it tries to curl around the top and the sides, but its effect is lessened as you step away from the leading edge of where the wind's hitting. So you can see that the magnitude of the force on the panels of the roof or the sides reduces, it steps away as you get further along the building. And finally, you can see the effect on a larger and more complex building. If I apply a north load on there, north wind, you can see obviously again the biggest effect is on the front face, a less effect on the rear, and for the roof and the sides, the effect pulls away from the building or upwards away from the building, but it steps back as you get further from the leading edge of the wind. And I can obviously change the direction. You can see how it affects these little cutouts and funny shapes. It can get pretty complex pretty fast. Now remember, this is all pretty basic wind. There are other effects that modify it in certain areas, like around corners of roofs and things like that, and corners of panels. So this is just the basic wind. So the next step is to work out where the wind load applies to the structural members. So for this I've got a simple parametric portal frame where obviously we can just adjust the framing as we need to pretty easily. So now I've turned on the automatic wind zones on this frame. You can see the distribution of the forces based on the direction of the wind hitting the frames. Now, one thing to note is that for this particular height, the zone lines up exactly with the frame, but that's a bit of a fluke because as I adjust the height of the building, the zones are going to change to suit. So for most of the time, the framing isn't going to line up with the zones. So when we come to distribute the wind distributed forces onto the frames, it's never going to line up perfectly, which I'll show you in the next step. And in the next step, I'm going to use vertically spanning cladding on the walls, and I'm going to span the roof in the Y direction. But bear in mind that the cladding on the walls could span horizontally as well, and the roof could even span the other way as well, although that's not common. So now I've got the forces on the actual members turned on, and as I was saying, the script works these out by applying these zones onto the framing based on the cladding spanning in the Y direction for the roof, for example. And to work out the size of these forces, it's taking half of this bay times this magnitude of force onto this frame. Then it's taking half of this bay times the magnitude of this force onto this frame, plus this piece here onto this frame, plus half of this magnitude onto this frame. So that's why it's less at the front, even though it's a higher force. It's only taking half a frame. And for the second one, it's taking only half of that bigger load, half of the second biggest load, but a full bay's width of load. So that's why it's higher. I'll turn that off again than the first leading frame. And obviously you can just, it'll automatically work it out for you. And for the cladding on the sides, it's, as I said, I've got it set to vertically spanning at the moment. So half of it will go into the ground, it's not shown here, and half will go to the span onto that rail or that side beam. And it obviously steps as the zones step. So if I turn on the zone for the roof again, that zone goes from there and it keeps going over the ridge. So the magnitude is equal for that extent, and then it steps down. That's why I've got a step in the force applied to the member. So these are the forces that the members are going to experience. And lastly, now we've calculated the forces on the members based on the automatic wind load zones, we can have a look how it's going to behave in a physics model. And of course all this is parametrics, so if we deleted one of these braced bays, we can see it deflects quite a lot more without that restraint. That stiffens it up a fair bit. And obviously we can add extra bays pretty easily, or change the size of the structure. Quickly get a feel for how it's going to move in the wind. Obviously this is exaggerated. In real life it's not going to be quite as bad as this, you would hope. Thanks for watching this structured parametrics video. Leave a like or subscribe if you found this useful, and we'll see you in the next one.